Thermodynamics, how to master COP energy input and output. Have you ever wondered how some systems can heat or cool spaces so efficiently? The secret often lies in the coefficient of performance, commonly known as COP. Understanding this concept can help you maximize energy efficiency in heating and cooling systems. Let's break it down. The coefficient of performance is a measure of efficiency for thermodynamic systems like heat pumps, refrigerators, and air conditioners. It is defined as the ratio of useful energy output to energy input. In simple terms, it tells you how much heating or cooling you get for each unit of energy you put in. To calculate COP, you can use this formula. COP equals desired output energy divided by required input energy. For heating systems like heat pumps, the desired output is the heat delivered to a warm space. For refrigerators or air conditioners, it is the heat removed from a cool space. When it comes to heat pumps, the formula is COP equals heat delivered divided by work input. For refrigerators, it is COP equals heat removed divided by work input. These formulas show that COP is all about the relationship between heat transfer and work input. A higher COP means better efficiency. For instance, if a system has a COP of 3, it means it moves 3 units of heat for every 1 unit of work input. That's impressive. The temperature difference between the hot and cold sides of the system plays a big role in COP. Smaller temperature differences lead to higher COP values because less work is needed to move heat across a smaller gap. Conversely, larger temperature differences can reduce COP, making the system less efficient. The design of the system and its components also matter. Efficient compressors, condensers, evaporators, and expansion devices can improve COP by minimizing losses and optimizing heat transfer. The choice of refrigerant is another important factor. Different refrigerants have varying heat absorption and releases characteristics, which can impact COP. Operating conditions like ambient temperature, humidity, and pressure can also affect performance. Systems tend to work best under favorable conditions. It is essential to note that the theoretical maximum COP is based on ideal thermodynamic cycles. Real systems will always have lower COP values due to practical limitations and irreversibilities. In practical terms, a heat pump with a high COP can provide more heat than the electrical energy it consumes. This makes it more energy efficient compared to direct electric heating. Similarly, a higher COP in refrigeration means less electricity is needed to maintain low temperatures, which can lower operating costs. To improve or master COP in real-world applications, consider these tips. Minimize the temperature difference between the heat source and sink when possible. Use well-maintained, high-efficiency components. Choose the right refrigerants for your specific operating conditions. Lastly, optimize your system design to reduce energy losses. By focusing on these aspects, you can better understand and improve the energy input-output relationship in thermodynamic systems. This makes the coefficient of performance a practical tool for evaluating and enhancing energy efficiency in heating and cooling applications.